Okay, so welcome everyone to the November's meeting. Today's speaker is Jan Zahalka, a researcher from the AI group led by Robert Babuška. And today's topic is hybrid intelligence. So without further ado, the stage is yours, Jan.
Okay, so thank you, Bara. My name is Jan Zahalka, and let's talk about hybrid intelligence. So first, what hybrid intelligence actually is. A definition that we could use is that it's an AI that interacts with a human during the learning/task execution process and learns from those interactions. If you would like a marketing equation form of this, you could say that HI equals AI plus human intelligence. And the motto is that we aim to assist humans instead of replacing them. And in this talk, I'm going to summarize my approach towards HI from the perspective of a person that does essentially applied machine learning and has multimedia analytics experience. HI is still an emerging discipline, and I am well aware that we have audience with diverse backgrounds, diverse approaches towards AI. And I know that AI or even HI does not equal machine learning, but I'm going to be speaking from my perspective, what I do. The invitation came at the right time, I'd say, because I'm now writing a personal grant application for HI. So I hope that I'll convince you that this is needed. So in the world of machine learning, it has been very dynamic over the last couple of years, and automated machine learning or AutoML approaches do already assist or complete tasks autonomously. And the automated approach has clear benefits. One variant is that the human is not needed at all, which reduces costs. And the second benefit is that the human can focus on the less menial tasks, which again reduces costs. Maybe you need 3 people to complete a certain set of tasks when you used to need 5 before. But it also can increase satisfaction, that the boring part of the job is done by an AI, so you can focus on something that is more fun. So why do we need HI then, if AutoML is so great? I'd like to tackle this from the task perspective, and I'd say that some tasks are indeed best suitable for AutoML, but others cannot really be solved by AutoML and need HI, and some would see improved results if we actually combine both approaches. To give you a couple of examples, I think that if you're writing a search engine, or if you're doing classification or regression on ontological data, or data which has very clear and crisp class definitions, then AutoML approach is probably the way to go. You collect your data, you train a classifier with those have good performance, and you're good to go. But if you do something like visual or multimedia analytics or intelligence on abstract or contextual semantics, then you might need HI, and this is where I'd like to make the case for HI in the subsequent slides. And the combination of both approaches could be used in, for example, shared autonomy, or from the more established machine learning, and in this case also computer vision tasks. Long tail classification or search could also, I think, be greatly helped by combining both worlds. So I'm not going to be focusing on the AutoML part. I'm going to be focusing on the HI and AutoML plus HI tasks in the subsequent slides. So visual multimedia analytics, to ground this as this task in terminology. If you have a domain of expertise, the expert may have an incoming data, possibly large data that is difficult to look through one by one, and the expert needs to gain insight into the data that she hasn't seen before and put it in context of her previous experience or education. An example of this would be forensics. So suppose that you seize a suspect's computer and you need to determine whether the person should be held beyond the 48 hours in jail. Another example, a particular one I've worked on, was forensic scientists monitoring certain suspicious websites for violent online political extremism or woke propaganda. They download hours and hours of video, and they have to see whether there's some incriminating content in a very large data set that they wouldn't be able to just watch through. Another example is medical sciences, looking for disease-related phenomena on a population. This has been that this is important has been demonstrated sufficiently with the situation around COVID, I'd say. Or from the more like entertainment domain, you could, another example would be sports. So you would do analytics of plays or tactics that are employed by various athletes or teams. But the domains of where this could be needed are vast. These are just 3 examples. An HI solution is an analytic system which has tightly coupled visualizations and model, machine learning model in my case, that provides on-demand intelligent assistance as the domain expert uncovers nuggets of insight. And the word insight itself is a bit of a buzzword, but I really like these definitions established in the visual analytics community already since 2006. That you define insight, the deep understanding, through 5 characteristics. Complex, insight is complex, involving all or large amounts of the given data in a synergistic way, not simply individual data values, which means you have to look through a large portion of the data set, if not the entire data set, to really gain understanding. Deep means that insight builds up over time, accumulating and building on itself to create depth. Insight often generates further questions and hence further insight. It's qualitative, it's not exact, it can be uncertain and subjective, keyword subjective here, and can have multiple levels of resolution. Unexpected, there's room for serendipity, it's often unpredictable and creative. And relevant is deeply embedded in the data domain, connecting the data to existing domain knowledge and giving it relevant meaning. It goes beyond dry data analysis that you just compute the stats of the data set and are done with it. We need relevant domain impact, maybe some decisions that need to be made based on the experts' handling of the data in an analytics system. So it's evident that here we need something flexible, interactive, where the system actually, or the model actually chases the expert's mental model and gives her what she needs to, well, attain insight, right? It's not something that can be pre-computed. To give you a couple of examples from my own previous work, this is called the New Yorker Melange. It's in venue recommendation. We have entered this into the ACM Multimedia Grand Challenge in 2014, which was about, it was literally do something cool about New York. So we created this system that where you select your, visually select your interests, and it matches you to users like you that go probably to places that you might like. So instead of looking for particular venues, you are matched to users that are anonymized. So we didn't really, this is not a dating site, right? It's really just that you can discover interesting venues in a more exploratory way. We have actually won the Grand Challenge with this. So this has been a success. Another more recent examples, we have published this this year in IEEE Transactions on Visualization and Computer Graphics. It's a general multimedia analytics system where you create categories called buckets. Here we have birds and flowers. And the underlying model, it interactively learns those buckets. So already you can see from 2 examples that the suggestions are pretty good. So the dashed lines with the particular color is the suggestion for the bucket, and this can be used for all tasks ranging from exploration to search on general multimedia collections. Another task that I've mentioned in the motivation intro was abstract or contextual semantics. So what is this? Well, sometimes you want to do AI or reasoning on semantics that are not objective or ontological or predefined, grounded, such that you can pre-compute, right? This can range from ad hoc compounds, such as boat on river. So yes, there has been some research on n-grams, but sometimes you could argue that you only use a very small portion of the n-grams. So the ad hoc compounds are very suitable for HI. But where we can definitely add value is feelings and or opinions, such if you want classes such as, or categories such as beautiful, stylish, or artistic. Doesn't make much sense for a computer science guy like me to assign labels, what is artistic, train a deep net, and then once and for all decide what is stylish or artistic, I think. And sometimes you have contextual classes such as suspicious. I've mentioned forensics research before. In forensics research, sometimes completely inconspicuous objects, such as this cup, if it makes it to a crime scene, it can connect people to places. So you need to be able to add this context to your analysis. And then there's also class discovery, such as who is COVID-19 vulnerable. we have seen lots of debate on this recently, or like XY's new sports tactics. So if there's like a team that has won the championship last year, they might have used some new plays that you need to categorize and you want to look for evidence in your data, possibly in your video data. So injecting the user's prior and personal knowledge and intent is very important. And HI can do this through a context dialogue between the human and the machine, which I'm gonna conceptually show a bit later. To further illustrate the point that data is not as objective as it might sound, I'm going to show an example from, again, the world of multimedia. So this is or in particular image data. So here on the left we see a nice picture taken on the Petrine Hill. We see something like nice spring/summer day, beautiful low light. It's a nice park we might want to visit. We might want to walk in. Kind of nice, right? And we see this instantly, whereas the machine only sees a matrix of RGB values by default, right? If you before you extract some kind of features from it. So in this picture, 15.1 million values in this one image alone. So there's evidently a discrepancy between the left side and the right side here, and it's a very well-known phenomenon. It's called the semantic gap. Is this disproportion between the information that is extractable by us humans and the information extractable by a machine from the machine representation of the same item, right? So you have things like that we can indeed extract complex/abstract semantics instantly, whereas the machine can only extract limited semantics, and it can take a bit of time. I mean, that it takes time is a bit contentious statement, right? So nowadays with modern deep nets, this is not such an issue, but keep in mind that this has been identified in the year 2000, so we've come a long way since then. But what is definitely true is that as humans, we can put it in context, whereas the machine does not have any context by default, unless we use it as some kind of prior knowledge. So there's this disproportion here, which is great progress has been made to close the gap, especially in recent years, but the gap is still there, right? So it's wobbly even on one item. So we have focused on one item, one image, the image of Petrine Hill. But then you have things like similarity. Similarity, of course, establishes structure on a collection. So let's consider this very simple case of a multimedia collection with 3 items. And ask the question, which image is the odd one out? Which one is the most distant from the others? And again, the answers may vary, right? Because the classic answer that you would get from computer vision researchers in around 2000 would be that it's the image of the queen, because the other two both contain a prominent red object, right? So you do a color histogram. The queen wears blue here, so she would probably come out as the one being the furthest away from the other two. Now, if you do something like a modern deep net that uses concepts, you could say that the phone booth is the odd one out because the other two both contain people. But also you could make a case for the Little Red Riding Hood being out, because if you're looking at the collection culturally, as far as I'm aware, Little Red Riding Hood is a continental story, whereas the other two are both related to England, right? So the point here is that already on this small collection, one could argue that structure is not inherent in the data, but it depends on context. So again, one more case for analytics or exploring data sets being handled interactively with hybrid intelligence, with the user being really involved in the learning process. Okay, so now I'm gonna move on briefly to the HI plus AutoML world, where we could improve things by combining stuff. Shared autonomy is an interesting case. So suppose that you have an autonomous agent or robot solving a task in an environment, possibly, I don't know, a decontamination robot trying to reduce some hazards in a contaminated area. The robots in the modern sense are generally based on reinforcement learning if they're using AI. So that's an AutoML component, definitely. And shared autonomy means that the agent works autonomously, but a human operator can at times intervene and point the agent in the right direction. So if we actually add HI to this, so if we make the robot learn from these interactions rather than just correcting it, then it may result in faster convergence of the model and more trust by the human operator or by the person that buys the robots, right? And it can open up possibility of semantic teaching of agents or robots. And I believe that this can be extended to analytics or software domains too. So for example, like write me a report about the data. There's an existing project now in the Netherlands by Professor Frank van Harmelen from the Free University of Amsterdam, where they have been granted an HI project about creating an HI scientific paper co-author, which I think is a cool idea. I'm going to be watching the progress of this project with great interest. And here's just an example of a very famous shared autonomy system. It's the Mars Rover, shared autonomy or mixed initiative, depends on the terminology, but for sure you all know this one. Finally, the long-tailed classification or search. The task here is doing meaningful search on semantic concepts that have few or no training examples. For example, we have an image database of plants, and we're looking for a plant that has only 3 images in the database. You can hardly train a deep net on this. You would have big trouble. So this is a known phenomenon. There has been great progress in recent years, for instance, through zero-shot and or transfer learning. But I believe that adding interaction could really inject some extra context knowledge and teach the model to discriminate the concepts better, basically going the last mile. So the auto ML part would narrow it down to the generally correct part of the collection, but then with some refinement through interactive learning, I think that you could find your fine-grained or long-tailed classes more easier. To demonstrate that this is needed, let's take, for example, the ImageNet dataset, which is probably the most famous visual recognition challenge dataset that is currently in existence. And these are the stats, so images per class and the number of classes. So it's a nice distribution graph. And we see that there are thousands of classes with insufficient training data for a conventional deep net. So if you only have 100 or less training images, we have 900 classes where you can hardly train something meaningful when we were speaking about modern auto ML models. So here we could really add some value. So to summarize the motivation, HI complements and or enhances auto ML. So I personally don't intend it to compete against auto ML strictly, but to unlock solving tasks that auto ML wouldn't solve alone or at all, or enhance its performance. I think that HI itself has 2 clear benefits, or I would even call it motivational pillars. One is explainable AI. So XAI is a big topic currently because the most modern models are usually black boxes, and humans, of course, want to understand why a decision was made. I'd argue that HI has a degree of explainability built in, because if we're leading a dialogue between AI and a human, there have to be meaningful interactions. So the interactions that help build the HI model have to make sense. And another benefit, or what I view as a benefit, because this is a bit opinionated, I do believe that AI shouldn't dehumanize. I dislike considering or treating users as cattle that is simply milked for data and then modeled anonymously, right? I think it's dangerous. I think that it's completely fine for specialized tasks with a clear singular purpose, but as AI becomes more general and more adopted in wide areas in our life, I do think it becomes an issue. HI is centered around the dialogue between the user and the machine, with the user's needs taking priority. So that's my bit of motivation, personal motivation, why I'm doing this, basically. Okay, so let's look a bit under the hood of HI. So what it is. As a person that has done visual and multimedia analytics, I'm going to start with, I think, a useful starting point, a visual analytics pipeline. You have your data incoming from the left side. Then you pre-process the data. You load it into the model and you load it into the visualization, because if we're in analytics, we have a user that interacts with the visualization through here. You can train the model and you can retrain the model. And the key arrows are the ones between visualization and model. So the visualization, the interactions that we receive from the user here, they drive the model retrains itself, and then the model drives the visualization further, brings the user, the expert, to parts of collection that he or she needs to see. And the resulting knowledge or insight, as I have called it in previous slides, is a product of the model state and the visualization. Then we can either complete the task, or we can realize that we need more data and further investigation. So we gather more data, and the process goes on. So this is visual analytics. So let's make it more like the HI pipeline. So to start, since HI equals AI plus human, then the model needs to be an AI model. And my flavor of HI, if I can call it that, would be that it's going to be a mostly machine learning model. So again, AI does not equal ML, but this is what I do. So note that in classic visual analytics, the model doesn't have to be AI. It can just be stats computed over the data. Well, one could also argue that machine learning is just applied statistics, but let's not go there. But I'm going to be doing this mostly with an ML model, or I have been doing this with mostly ML models. The next thing that you need to do is that we need to generalize visualization to an interface, right? Because yes, you do use visualization in the analytics sense, but if we're also looking into task completion, then we need to have a general communication interface, I would say, or you can imagine it as an API or as an extra layer below the interface, possibly. Then I'd like to again stress that these two arrows are very important, because the model indeed must learn from what's communicated and drive further communication or further action. That's the core definition of HI. Again, we are not necessarily looking for analytic knowledge. We just need a result, which can be either analytic knowledge, or it can be certain task completion of the, let's say, of the semi-autonomous robot, for instance. So, and if I would have to draw my research focus or research agenda, it would be the blue highlighted parts here. So, and again, to give you a bit of an overview, so I've mentioned the term interactive learning a couple of times. Hopefully, so I would like to go into the detail here a bit, but I hope I didn't. It wasn't too confusing on the previous slides. Again, a very high-level overview. I think it's a good starting machine learning vehicle for HI. It was quite hot in the 2000s. It has fallen out of favor in the last decade, mostly due to great performance of deep nets. It was not needed, and collection size explosion, because if it's interactive, then it needs to be responsive. And if your collection is not 10K items anymore, but 10 million, then you might have a bit of problem. It has been innovated in late parts of the last decade for current collection sizes. So that's the good news. And the next focus is we want better performance and interfacing with AutoML. So what it actually is. So first, you have to extract features if you need to, typically using the deep net, especially in the multimedia context these days. So you project the data for visualization here into two abstract dimensions, let's say using a PCA or UMAP. Then you have, so the data is unlabeled. That's also very, very important to say. Then you have a user label a couple of examples as relevant or not relevant. Then what you do is you train the interactive learning model that separates the two. Then what you need to do is you need to go over all the unlabeled items and assign labels and scores. So now the classifier believes something is positive and something is negative, relevant or not relevant. And then you need to produce a set of candidates to be labeled by the user in the next round. But which out of the unlabeled data should you actually choose? There are two strategies for this. One is called relevance feedback. So you show the ones where the model is most confident, such that the user gets the most likely relevant results. Those are, in this simple case with a hyperplane or with like an SVM, would be the two furthest away from the hyperplane in the positive region. The other tactic is called active learning, where you show the ones where the model is least confident, so that your model converges faster. And basically, that's it, right? Those are the interaction rounds, and you repeat steps 2 to 5 until you're done, or until the user thinks he or she is done. And steps 3 to 5 need to complete in a maximum of 1 to 2 seconds, roughly, because and that's a big burden when we're talking large data sets, because so that means you have to train the model, go over all the data to assign scores, so that you're able to produce a set of candidates for the next round. So you need to complete these 3 steps very rapidly. Otherwise, it's not interactive learning. If it's not responsive, the user will quickly abandon the session. Briefly about my existing scientific results. So on the right, you see the cover for my PhD thesis. Most of the results are in the thesis. Some are beyond. So we have created an integrated multimedia analytics theoretical model. We have done an application in venue recommendation. That was the New Yorker melange that you have seen earlier. Then there has been an evaluation framework called Analytic Quality. We have scaled interactive learning up to 100 million images with response time of 1 second. The original system was called Blackthorn. That's the one that's in the thesis. Now I'm working on a system called Exquisitor in collaboration with the University of Amsterdam and the IT University of Copenhagen. And we have also seen the example, the general multimedia analytics system for exploration and search, the II-20. So what I'd like to do in the foreseeable future, so I'd like to create a generalized HI interface and richer interaction dictionary that supports a broad array of HI tasks. So because now the interactions are a bit, you know, how to say, laconic. Now we just say, okay, mark relevant and not relevant items. Maybe there is a broader interaction dictionary to be exploited. And also what slows down the research a lot is that for each actual application, for each system, you have to write a custom UI or API. You know, so you write a model, then you need to write an interface for the model, which then takes time. So if we have something general, then it would allow quicker prototyping of the actual HI models. Another point on my agenda is that we actually want to create new interactive machine learning algorithms and/or models, because the state of the art currently is pretty much linear SVM on top of features that are extracted by a deep net. So RQ1, can we do better? Research question 2, how do we split online and offline computations, because you cannot compute everything online, and which model types allow meaningful interplay between each other. Another big issue is evaluation. So how do we evaluate an HI approach, and especially in the design phase? The user if you have a user, you should be doing a user study, of course, but those are suitable for whole systems rather than algorithm or model prototypes, and usually only towards the end of design or towards the end of a major design cycle. And if you have benchmarks, which are crisply defined and repeatable and just convenient, they do not take users into account at all. So we have done some work with the analytic quality interface. I have put a reference at the end of the presentation, so whoever's interested in this can consult the reference, but more needs to be done. So this is still on the agenda. And of course, I had semi-autonomous in the title of this talk. So semi-autonomous HI, where the model proceeds with the task autonomously, the human interacts according to the task's needs or their wishes, and the model will be learning from the human and providing a timely response. This is, of course, inspired by shared autonomy, but it also taken to other tasks such as summarization or active learning, so that you have like this agent running on your data, and it will complete the task for you, and you just oversee it. I have conceptualized this on what I call the autonomy axis, where on the left side you have essentially AutoML. So you have full autonomy, where agents are pre-trained and make decisions based solely on the training. The right extreme is full interactivity, or you could say interactive learning, as was presented before, where the agents train online on user interactions, and all they do is that they just react intelligently to the user. And I think there is a whole space between these two, and anything beyond the leftmost extreme is fair game for HI and could result in some interesting applications, in my opinion. Okay, so to conclude, hybrid intelligence is an AI that learns from the user's interactions during the learning/task execution phase. It unlocks AI assistance in several useful tasks and potentially enhances AutoML approaches in others. I believe that there are many research opportunities coming up in the foreseeable future, and I'd like to thank you for your attention. Looking forward to your questions, and if you're interested to talk about this in more detail, then let's for sure have a chat. Drop me an email or contact me via other means, and I'll be happy to chat with you. Thank you, guys.